Greetings to all. I am A. Mohamed Ali, Assistant Professor, Department of Mathematics, GTN Arts College, Dindigul. So, in this lecture video, we are going to see isomorphism on groups. Definition: an isomorphism phi from the group G to a group G dash is 1 1 and on 2 mapping that preserves the group operation pi of xy is equal to pi of x into pi of y. If G is isomorphic to G dash, then we denote it by G isomorphic to G dash. So this is the notation for isomorphism. Then some of the examples of isomorphism. First example, let us consider a group G is the set of all real numbers. So we know that set of all real numbers forms a group with respect to addition, and G dash is set of all positive real number is a group, form a group with respect to usual multiplication. With the two groups, then pi is a mapping from G to G dash as pi of x equal to 2 power x. So it's an isomorphism. So according to the definition of isomorphism, we have to prove pi is 1 1 and pi is on 2 and pi is homomorphism. First we have to prove pi is 1 1. Let pi of x equal to pi of y. Then according to the definition of pi, we can replace pi of x by 2 power x and pi of y by 2 power y. Okay, so dividing both sides by 2 power y, so we get 2 power x minus y equal to 2 power y by 2 power y is 1. So 1 can be replaced by 2 power 0. If the bases are equal, we can compare the exponents. So x power y equal to 0. From this we get x equal to y. Therefore f is 1 1. Then definition of onto, let us choose one element in the codomain. So the codomain is what? G dash. G dash is r plus comma dot. So I am taking y in the codomain r plus. Then there exists an element x in the domain log 2y such that pi power x is equal to 2 power x. Substitute x is equal to log base 2y. We know that 2 power log base 2y is what? Y. Therefore pi is onto. Then pi is a nice homomorphism because pi of x plus y is equal to 2 power x plus y, and we can write 2 power x plus y is equal to 2 power x into 2 power y and replace 2 power x by pi of x because pi of x equal to 2 power x. So 2 power x is equal to 2 power x can be replaced by pi of x and 2 power x can be replaced by pi of y. Therefore pi of x plus y equal to pi of x into pi of y. Therefore pi is homomorphism. Then next example of isomorphism. So let us consider the group G, where here G is set of a special linear group or the set of all 2 cross 2 real matrices whose determinant is 1. Okay, so let us consider the mapping pi from G to G dash as pi of A is equal to M inverse. So actually the conjugate of A, actually pi is what? The conjugate of A. Conjugate of pi of A equal to M inverse. So M inverse is a conjugate of A. So for all A in G, where M is the fixed 2 cross 2 real matrices in SL of 2 comma R. Then pi, we have to prove pi is isomorphism. So for now, let us consider pi is 1. Now let us consider the mapping pi. We have to prove that pi is 1 1. So let pi of A equal to pi of B. Then pi, according to the definition of pi of A can be written as M inverse, and pi of B can be written as M inverse. Now pre and post multiplying by M inverse and M on both sides, we get A equal to B. Therefore pi is 1 1. Now we have to prove pi is onto, and let us choose a matrix A in G. Then there exists a matrix M inverse AM belongs to G such that pi of M inverse AM is equal to M into M inverse AM into M inverse. This comes from the definition of pi. Definition of pi is what? You have to pre-multiply by M and post-multiply by M inverse. So what is the element in pi here? M inverse AM. So we have to pre-multiply by M. So M into M inverse AM and post-multiply by M inverse. So M into M inverse AM into M inverse. So first you have to composite the first two elements. M into M inverse is identity matrix and M inverse is identity matrix. Therefore I. So I is what? A. So then phi is homomorphism. So let us take pi of AB. So pi of AB is equal to what? M inverse. Now insert M inverse M between A and B, because M into M inverse is identity. So we can insert the identity matrix between A and B. So MA, M inverse, MB, M inverse. Now grouping the first three elements, MA, M inverse is what? According to the definition of pi, we can replace MA, M inverse by pi of A. And obviously, the last three elements can be replaced by what? Pi of B. So pi of AB equal to pi of A into pi of B. Therefore, pi is homomorphism. Therefore, pi is 1, 1, onto and homomorphism. So we can say that pi is isomorphism. This is a special type of isomorphism. It is called conjugate by M. Okay. Next example of isomorphism. Now let G is equal to 1 comma omega square. So we know that 1 comma omega square is what? The cube root of unity. Omega cube is equal to 1. So G is a cube root of group of cube root of unities, and G dash is the group of rotation in a plane through 0 degree, 120 degree, and 240 degree. So the rotation by 0 degree is called R0, and the rotation by 120 degree is R1, and similarly the rotation by 240 degrees R2. Now I am assigning the mapping pi theta from G to G dash is given by pi of 1 goes to R0, pi of omega goes to R1, and theta of omega square goes to R2. So it defines an isomorphism G onto G dash. Next, some of the properties of isomorphism. Let us consider the mapping theta from G to G dash be an isomorphism of G onto G dash. Let E and E dash be the identity element of G and G dash respectively. Then the first property, theta of E is equal to E dash. We know that the E is an element of the domain. E belongs to the group G, and E dash is an identity element of the group G dash. Now we have to prove the mapping of E goes to E dash. That means the identity element in the domain G goes to the identity element in the codomain. So let I am taking theta of E equal to A dash. So why I am putting dash here? Because I am differentiating which element is belongs to the domain and which element is belong to the codomain. So whenever you put it the dash, that element should be belongs to the codomain. So theta of E is equal to A dash. So A dash belongs to the codomain G dash. Now A dash belongs to A dash is equal to theta of E, and we can write E as E into E because E is an identity element. How many times you can multiply E? The result is E. So we can replace E by E dot E. Theta is an isomorphism because it is a given in the problem. Theta is an isomorphism. So we can write theta of E dot E as theta of E into theta of E. Theta of E is A dash. So we get A dash into A dash. Thus A dash into A dash is equal to A dash. So from this statement, we get A dash into A dash is A dash. So A dash into A dash is equal to A dash. A dash is replaced by A dash into E dash. E dash is an identity element in G dash. So by cancellation law, by left cancellation law, we get cancelling A dash and A dash on both sides. We get A dash equal to E dash. Now replace A dash by E dash in our assumption. What is our assumption? Theta of E is equal to A dash is our assumption. So replace A dash by E dash. We get theta of E equal to E dash. Hence the proof. So proof 1 is over. Next one, we have to prove theta of A inverse equal to theta of A the whole inverse for all A in G. Proof theta of A inverse into theta of A. We have to prove theta of A inverse into theta of A equal to E dash, as well as theta of A into theta of A inverse equal to E dash. Then only we can say theta of A inverse is the inverse of theta of A. Okay, so theta of A inverse into theta of A can be written as theta of A inverse into A because theta is isomorphism. So we can write like this. So A inverse into A is what? E. So theta of E is in what we have proved in the previous step. Theta of E equal to what? Theta E dash. So theta of E equal to E dash. Similarly, we can prove theta of A into theta of A inverse equal to E dash. Hence, by the uniqueness of inverse of G dash, theta of A inverse is the inverse of theta of A. I hope you all understand well. Next, in the above properties, the result is valid even if theta is in 1, 1 and homomorphism. It need not be onto. So in the previous case, F is 1, 1 and homomorphism. So we have not used that onto property in the previous proofs. So theta is need not be onto. Right. Then for all n is belongs to Z. Next property of isomorphism, very important property and obvious also. So for all n is belongs to Z and for all A in G, theta of A power n is equal to theta of A whole to the power n. Suppose here we have taken 3 cases. First one, suppose n is 0 and n is belongs to the set of all positive integer. And third case, if n is belongs to set of all negative integers. Suppose when n is equal to 0, theta of a power 0 equal to what? Theta of 1. So 1 is the multiplicative identity. So in general, we can write theta a power 0 is e. So theta of a power 0 equal to theta of e, that is equal to e dash. And also theta of a whole to the power n. So I am taking the left hand side and put n is equal to 0. Theta of a whole to the power n is what? Theta of a whole to the power 0. So anything power 0 is what? 1. Theta of a is an element in the codomain. So that's why we can write the element in the identity element in the codomain is e dash. So theta of a whole to the power 0 is what? E dash. So therefore theta of a power 0 is e dash, and theta of a whole to the power 0 is e dash. Therefore theta of a power n equal to theta of a whole power n. And case 2, when n is belongs to set of all positive integer, so theta of a power n equal to theta of a into a up to n times. We have to multiply a by n times. So theta is an isomorphism, so we can write theta of a into theta of a up to theta of a. So how many times we have theta of a? There are n times, so we can write theta of a whole to the power n. Then case 3, suppose n is belongs to the set of all negative integers. So we can choose n is equal to minus m, where m is belongs to integer. Theta of a power n equal to theta of a power minus 1, because we have to replace n by minus m. So theta of a power minus m is equal to what? Theta of a inverse whole to the power m. So that means we have to multiply the inverse element of a by m times. So and a inverse theta of a inverse whole to the power m is same as theta of a whole to the power minus m. By law of exponent, we can write like this. So theta of a whole to the power minus m, and replace minus m by n. So finally we get theta of a whole to the power n. What is the left hand side? Theta of a power m. The right hand side is theta of a whole to the power m. So hence we have proved theta of a power n is equal to theta of a whole to the power n. Okay. Next theorem, some theorems we are going to discuss some theorems on isomorphism. Let G and G dash be isomorphic. What is that meaning? G and G dash be isomorphic means there is a mapping, isomorphism mapping between G and G dash exists. And if G is abelian, so is G dash. So if G is abelian, we have to prove G dash is also abelian. Let us consider the mapping theta from G to G dash, the isomorphism of G onto G dash. Let choose two elements, a dash and b dash in G dash. Since theta is onto, there exists a in G and b in G such that theta of a equal to a dash and theta of b is equal to b dash. Now a dash into b dash is equal to a dash. We can replace a dash by theta of a, because we are assuming a dash is theta of a and b dash is theta of b, because a dash and b dash are the images of a and b from the domain to the codomain. Now theta is isomorphism here, so naturally we can write theta of a into theta of b equal to theta of ab, and a and b are the elements in the domain. Domain is abelian, so according to the commutative property we can write ab as ba. So theta of ab is same as theta of ba since G is abelian. So theta of ba, how we can write theta of ba? Theta of ba is equal to theta of b into theta of a, because theta is isomorphism. Obviously it is homomorphism. So theta of b into theta of a. So theta of b is b dash and theta of a is a dash. So what we have obtained from this step, a dash into b dash is equal to b dash into a dash. Therefore G dash is abelian. So in the above theorem also is true if theta is onto homomorphism and G is abelian and G dash is non-abelian, then G and G dash cannot be isomorphic. So that is a very important remark. So if both are abelian, the theorem is true. Suppose if G is abelian, G dash is non-abelian, then G and G dash cannot be. There does not exist any isomorphic map between G and G dash. Next theorem, any infinite cyclic group is isomorphic to Z, and any finite cyclic group of order n is isomorphic to Z power n. So what we have to prove here, any infinite cyclic group is isomorphic to the set of all integers, and any cyclic group of order finite order n is isomorphic to Zn. Now, okay, I am taking the case 1. In case 1, I am assuming G is an infinite cyclic group. Let G is an infinite cyclic group. We know that every cyclic group has some generator. Here I am considering G is equal to the generator of A. So here A generates the group G. Okay. So now define a map F from the set of all Z to the group G is given by f of n equal to a power n. So what it means actually, that f of n is every element in the domain can be written as some integral power of a. So f of n equal to a power means every element in the domain is z, every element in the domain is z. We can write that images some exponent of positive integers. Okay. So according to the definition of f, we can write f of m plus n equal to a to the power m plus n, and write a power m plus n equal to a power m into a power n, and replace a power n by fm by definition of f, and a power n replaced by fn. So f of m plus n equal to f of m into f of n. So naturally it is homomorphism. Therefore f is homomorphism. Since all the powers are distinct in G, therefore f is 1 1. So if all the powers of n is distinct because we are choosing some element from the z. Okay, because n is, we are assigning some integral power of n, so each exponent is, each power is distinct, therefore f is 1 1. By definition it is onto, hence G is isomorphic to z. Now I'm next in the next case I am considering G is a finite cyclic group of order n. So G equal to generator A such that order of A equal to what? N. Let f from Zn to G is defined by f of k dash is equal to a power k, and f is well defined. Then L dash plus M dash is equal to K dash if and only if L plus M is isomorphic to K into mod n, where 0 less than or equal to K less than or equal to M minus 1. If and only if L plus M minus K divides N, if and only if L plus M minus K is a multiple of N, and if and only if a power L plus M minus NP equal to a power K. Now we can write a power L plus M minus NP as a power L plus M into a power N whole to the power minus P, and we know that a power N is E, so a power L plus M into e power minus P power anything is E, so a power L plus M equal to a power K. So if and only if a power L plus M equal to a power K. A power L plus M can be written as f of L dash plus M dash, that is equal to a power K can be written as f of K dash. So f of L dash plus M dash equal to f of K dash, that implies a power K equal to a power L plus M, and we can write a power L plus M by the law of exponent. A power L plus M can be written as a power L into a power M, and a power L is replaced by f of L dash, and a power M replaced by f of M dash. So hence f of L dash plus M dash equal to f of L dash into f of M dash. F is homomorphism. Suppose L dash is not equal to M dash, implies L is not equal to M, and a power L is not equal to a power M, that implies f of L dash is not equal to f of M dash. So what we have assumed here, L dash is not equal to M dash, what we have obtained, f of L dash is not equal to f of M dash. So this is the definition of onto, hence f is 1 1. I think this is the definition of, this is the definition of 1 1. So if L dash is not equal to M dash, then f of L dash is not equal to f of M dash, that means f is 1 1. Clearly f is onto, and f is an isomorphism, hence G is isomorphic to Zn. Then on corollary, any two cyclic group of same order are isomorphic. So we can prove this corollary from the previous theorem. Let G and G dash be a finite cyclic group of order n, then Z is isomorphic to Zn, then automatically Z dash is isomorphic to Zn by the above theorem. Therefore, G is isomorphic to G dash. Then case 2, if G and G dash are infinite cyclic groups, by previous theorem, G is isomorphic to Z and G dash is isomorphic to G dash is also isomorphic to Z dash. Then therefore, G is isomorphic to Z and G dash is isomorphic to Z. The Z dash means what in the left hand sides are, the right hand sides are equal, then automatically the left hand sides are obviously equal. So G is isomorphic to G dash. So some remark: if each prime P, there exists only one group up to isomorphism of order P, that is the cyclic group of order P. Where P is a prime here. Then the first theorem on isomorphism, let f from G to G dash be a homomorphism of G onto G dash, and the kernel of f is K. Then G is normal in G, K is normal in G, and G over K is isomorphic to G dash. Proof: let f consider the map f dash from G over K to G dash be defined as f dash of AK. Here AK is equal to what? F of A for A in G. Now let us consider AK equal to BK. Then actually it is a coset. AK equal to BK is a coset. Then we can write as if and only if A inverse B. I think pre-multiplied by A inverse on both sides, we get A inverse B is belongs to K. The if and only if A inverse B if A inverse B is belongs to K, we can write f of A inverse B equal to E dash. If and only if, according to the definition of f is homomorphism. So we can write f of A inverse B as f of A inverse into f of B, that is equal to E dash. So if and only if f of A inverse into f of B equal to E dash, if and only if f of A equal to f of B, if and only if f of A is equal to f dash of AK, that is equal to f dash of BK. Therefore, f is well defined and 1 1. Since f is onto, so f dash is also onto. F dash of AK BK equal to f dash of A BK, because product of two left coset is again a left coset. So f of ak bk equal to f dash of ak abk. Then f dash of abk is equal to what? F of ab, and f of ab can be written as f of a into f of b. So and f of a is can be written as f dash of ak, and f of b is can be written as f dash of bk. Therefore f dash is a homomorphism and f dash is 1 1 and on 2 as well. Hence f is isomorphism. Therefore g over k is isomorphic to g dash. Hence the proof. Then next lemma, let f from g to g dash be a homomorphism, then k is a subgroup of g and f of h is a subgroup of g dash when f is homomorphism. H is a normal in G and F is onto, then H dash is a normal in G dash. Suppose if H dash is a subgroup of G dash, then F inverse of H dash is equal to H. Then F inverse of the inverse image of subgroup is also a subgroup of G. Then H inverse is normal in G dash. That implies H is a normal in G. Further, if F is onto, then G over H is isomorphic to G dash over H dash. In second theorem of isomorphism, let H and K be the normal in G and K is a subset of H, then H over K is normal subgroup of G over K, and G over K by H over K is isomorphic to G by H. Now consider the projection map P from G to G over K, that is equal to G dash. By the definition, we are taking P of A equal to AK, where A is belongs to G. Since H is a normal in G, then P of H is equal to H over K, and H over K is what? H dash. Consider G over K is equal to the set of all cosets or left cosets AK such that A belongs to G, and H over K equal to set of all left coset AK where A belongs to H. Here in the first set, A belongs to the group G, in the second set A belongs to the group H. So obviously H dash is normal subgroup of G dash. Then the third theorem of isomorphism, let H comma K is a subgroup of G with K is a normal in G, then H intersection K is a normal in H, and H over H intersection K is isomorphic to HK by K. Since K is normal in G and K is subset improper subset of G, therefore HK is a subgroup of G. If then that implies HK equal to KH. As we know, as K is normal in G and HK is a normal, HK is a subgroup of G and K is a normal in KH. That implies HK over K is well defined. And also H intersection K is normal in H. And let us consider one element X belongs to H intersection K. So if element belongs to the intersection, that element should be present to each group. So X belongs to H and X belongs to K. Since H belongs to H, therefore H inverse belongs to H. Since K is a normal in G and X belongs to K, therefore H inverse belongs to K, and hence H inverse belongs to H intersection K. Then F is function from H to HK by K by F of A equal to AK. Therefore XK belongs to HK by K. Then XK is equal to HK of K. Then HK of K is HK. So that is equal to F of H. For some H belongs to H and K belongs to K. Therefore F is on to. Then F of AB equal to ABK. ABK can be written as AK into BK. So AK is what? F of A, and BK is F of B. So F of A into F of B. Therefore F is homomorphism. And the kernel of F can be written as set of all A in H and F of A equal to K. That is equal to set of all A in H such that whenever FA belongs to FA is equal to K, AK equal to K. So AK equal to K means A belongs to K. Therefore, set of all A in H such that A belongs to K. That is actually the definition of H intersection K. Therefore, the first theorem of isomorphism theorem, we can write H by H intersection K is isomorphic to HK by K. Thank you.